Now let's go ahead and start finding some of the features of our hyperbolas. And this should say hyperbola. So we want to identify the center, the vertices, and the foci. That means we need the values of h and k, we need a, and we need c. Then we want to identify the asymptotes. The asymptotes also require h and k, but then they also require a and b. So we need a, b, and c as well as h and k in order to find all of these features. First things first, we need to get the equation in the standard form. If you notice, the square's already been completed. So all we have to do is get the equation set equal to 1 so that we can finish simplifying it in its standard form. So when we reduce each of these fractions, when we divide by 36, we get x minus 1 squared over 9, y minus 3 squared over 4 equals 1. So now we're in standard form. We can look at identifying some of the key features. We know the value of h is 1. We know the value of k is 3. A squared is 9, which means that a is 3. B squared is 4, meaning b is 2. Then we can use our Pythagorean relation in order to calculate for c. And so we get 13 for c squared. So we know c is the square root of 13. So now let's visualize our hyperbola. So since it's x squared is first, it means we have our horizontal axis hyperbola with our center and our vertices on the side. So the vertices will be a units to the left and the right. So 3 units to the left and right of center. So if we start with center, we know center is h and k, 1, 3. To get our vertices, we want to go 3 units left and right. That's going to change the x values. So we're going to be adding and subtracting 3 from the x value and leave the y value alone. So we'll have the points 4, 3 and negative 2, 3 for our vertices. So we use a to get the vertices. Then we can go ahead and identify our foci. Foci uses the c value. And the foci go in the same direction as the vertices, but they're going to be further out. And c has to be a further distance. So using our c value, we're going to go the square root of 13 number of units left and right from the center. And that's going to be approximately 3 point something. So we have 1, and we're going to add and subtract the square root of 13 from the x value. The precise locations will be 1 plus the square root of 13 and 1 minus the square root of 13. If you need to actually plot the points, you'll have to use rounded values. And since the square root of 13 is approximately 3.6, you would just add and subtract 3.6 from the x value and get your location of 4.6, 3 and negative 2.6, 3. So those would be rounded locations. Last thing they ask for is the asymptotes. So the tricky thing with the asymptotes is just considering what's the slope. So let's look at our diagram. If I have an imaginary line that's running through, and my a value is this horizontal distance, I need to consider what the vertical distance is for the run, or for the rise. Well, since a is the horizontal distance, b has to be the vertical distance. And so my slope is going to be b over a. So we'll use b over a, x minus h plus k. So our b value was 2, our a value was 3, h is 1, and k is 3, and there's our two asymptotes. So we were able to identify our center, our vertices, our foci, and our asymptotes. Now let's go ahead and do the same thing for part B. Now here, the square hasn't been completed, so we need to do that on our own. So we'll group our x terms as well as the y terms. Make sure the positive squared term goes first, since now one of them will be negative with subtraction. So we group our x and y's, and then we move our constant to the other side. Now before we add our boxes, we have to factor out these leading coefficients. So we have x squared minus 4x, and we have our box. Now we need to be careful because we're factoring out a negative 4, which not only changes this to a positive y squared, but also changes the second term into a negative 2y. We also have to consider that on the right side of the equation, we'll multiply one of the boxes by negative 9, but the other box will be multiplied by negative 4. And so we have to make sure that we pay very close attention to these sign changes, otherwise we're going to end up with the wrong values inside of our equation, as well as the constant will be off. So we can complete the square. So we got 4 in these boxes and 1s in these. So we get x minus 2 squared, y minus 1 squared, and then when we multiply all of this out, we end up with 36. Divide everything by 36. And then again, we look at the shape of our hyperbola. Since x is first, it's a horizontal axis again. We know the distance to the vertices will be left and right, a number of units. Our foci will be left and right, c number of units. Looking at our equation, h equals 2, k equals 1, a squared is 4, so a is 2, b squared is 9, so b is 3, a squared plus b squared equals c squared. We end up, since it's the same values as before, we end up with c being the square root of 13. So again, we'll start with our center, this time located at 2, 1. Our vertices, again, we're going left and right, a units. And since a is 2, we're going 2 units to the left and the right. So when we subtract 2 from x, we get 0, 1. When we add 2 to x, we get 4, 1. Our foci, again, we're going left and right, c number of units. C is the square root of 13. So we'll add the square root of 13 to 2, and we will subtract the square root of 13 from 2. If we wanted approximate locations to actually plot the points, we would do the operation of addition and subtraction and use the rounded value of the square root of 13. And then our asymptotes. Again, our asymptotes have a rise of b and a run of a. So our slope will be b over a, and then x minus h plus k. Since our b value is 3, a is 2, x minus h, which is 2, plus 1 for k for our asymptotes. And there's all of our features. Lastly, we're going to find the equation given the features. It's really helpful to start with a diagram to understand the orientation of your hyperbola. If I have a center located at 2, 3, a vertex at 0, 3, and then a focus at 5, 3, we can see that I've got vertex, focus, and center all in a line, which means my hyperbola is going to be opening on the horizontal axis. So we'll want to use the equation that has the horizontal axis hyperbola. So x will be first along with a. So we need to find the values of h, k, a, and b in order to get all of the things for our equation. So starting with h and k, since our center's at 2, 3, we have those values. H and k, 2 and 3. Then we want to find a. A is from center to vertex. So since our center's at 2, 3, and our vertex is at 0, 3, those two units have a distance of 2. So a equals 2. If you had some different points that were a little bit further apart or harder to calculate, you could use the distance formula. Recall that the distance formula for any 2 points is the square root of the difference in the x values squared plus the difference in the y values squared. Plug in your 2 ordered pairs and you can calculate for the distance. Now b is going to be this conjugate length. We don't have any way to find b, but because we're given the focus, we do have a way to find c. So center to focus, that's our c value. And our center and our focus are 3 units apart. So c equals 3. We can now use our Pythagorean relation to find what b equals. If a squared is 4, c squared is 9, b squared equals 5, b is the square root of 5. So now that we have the values of a, b, and h and k, we just need to plug them into our equation. X minus h squared over a squared, y minus k squared over b squared equals 1. And there's our equation. We can do one more time. Again, we want to draw a diagram to start. We have our vertices. So here we're given a vertice at 0, negative 5, as well as one at 0, 3, and then 0, negative 6, and 0, 4 for the foci. So here we have a hyperbola that opens vertically. So we'll use the formula where y is first. A is still first. So we're not given our center, but our center is going to be the midpoint between either the vertices or the foci. And you can use either one. So our midpoint formula, we're finding the average of the x values and the average of the y values. So we take 0 plus 0 divided by 2, negative 5 plus 3 divided by 2, and we end up with a center at 0, negative 1. Then we can calculate a. The distance from 0, negative 1 to 0, 5 is a distance of 4. We can also calculate the value of c. The distance from 0, negative 1 to 0, negative 6 is a c value of 5. So using a squared plus b squared equals c squared, 16 plus b squared equals 25, b squared equals 9, so b equals 3. So we have a, we have b, we have h, we have k, we have everything we need for our equation. Y plus 1, since k is negative, y plus 1 squared over a squared, which is 16. Since it's x minus 0, we don't need to include it. It's just x squared. B squared is 9, equals 1. Lastly, we want to be able to look at an equation in general form and be able to quickly identify which conic section it is. So we can look at this identification here. Our parabolas are only going to have an x squared term or a y squared term, and the other one will not be squared. And so if we look at these equations on the side, example C, we see that y is not squared in this equation, which means that this has to be a vertical axis parabola. That's going to look something like that, with that vertical axis. Circles, x and y terms are squared and they have the same positive coefficient. Well, it's kind of hard to tell from these, but we need to get the variables on the same side of the equation. And so if we go ahead and get these closer to general form, and we move the variables all to the same side, we can see that for neither of these do we have the same positive leading coefficient. So neither of these can be circles. Circles would have to have the same positive leading coefficients. Often we see that there's no coefficient, but even if there is a coefficient, if it's the same, we still have a circle. Now, ellipses, x and y terms, they can have different coefficients, but they both have to be positive because an ellipse is plus. And so since we're adding here, we know that this has to be an ellipse. However, with the hyperbola, since we're subtracting, we know that we're going to have a hyperbola. And that's how we identify what our conic section is based on the form and the structure of the equation. And that's it for all of our conic sections.